Electrical element. Electrical elements are conceptual abstractions representing idealized electrical components, such as resistors, capacitors, and inductors, used in the analysis of electrical networks. All electrical networks can be analyzed as multiple electrical elements interconnected by wires. Where the elements roughly correspond to real components, the representation can be in the form of a schematic diagram or circuit diagram. This is called a lumped element circuit model. In other cases, infinitesimal elements are used to model the network in a distributed element model. These ideal electrical elements represent real, physical electrical or electronic components, but they do not exist physically, and they are assumed to have ideal properties, while actual electrical components have less than ideal properties, a degree of uncertainty in their values, and some degree of nonlinearity. To model the nonideal behavior of a real circuit component may require a combination of multiple ideal electrical elements in order to approximate its function. For example, an inductor circuit element is assumed to have inductance but no resistance or capacitance, while a real inductor, a coil of wire, has some resistance in addition to its inductance. This may be modeled by an ideal inductance element in series with a resistance. Circuit analysis using electric elements is useful for understanding many practical electrical networks using components. By analyzing the way a network is affected by its individual elements, it is possible to estimate how a real network will behave. Types. Circuit elements can be classified into different categories. One is how many terminals they have to connect them to other components. One-port elements, these represent the simplest components that have only two terminals to connect to. Examples are resistances, capacitances, inductances, and diodes. Multiport elements, these have more than two terminals. They connect to the external circuit through multiple pairs of terminals called ports. For example, a transformer with 3 separate windings has 6 terminals and could be idealized as a 3-port element. The ends of each winding are connected to a pair of terminals which represent a port. 2-port elements, these are the most common multiport elements, which have 4 terminals consisting of 2 ports. Elements can also be divided into active and passive. Active elements or sources, these are elements which can source electrical power. Examples are voltage sources and current sources. They can be used to represent ideal batteries and power supplies. Dependent sources, these are 2-port elements with a voltage or current source which is proportional to the voltage or current at a second pair of terminals. These are used in the modeling of amplifying components such as transistors, vacuum tubes, and op-amps. Passive elements, these are elements which do not have a source of energy. Examples are diodes, resistances, capacitances, and inductances. Another distinction is between linear and nonlinear. Linear elements, these are elements in which the constituent relation, the relation between voltage and current, is a linear function. They obey the superposition principle. Examples of linear elements are resistances, capacitances, inductances, and linear dependent sources. Circuits with only linear elements, linear circuits, do not cause intermodulation distortion and can be easily analyzed with powerful mathematical techniques such as the Laplace transform. Nonlinear elements, these are elements in which the relation between voltage and current is a nonlinear function. An example is a diode, in which the current is an exponential function of the voltage. Circuits with nonlinear elements are harder to analyze and design, often requiring circuit simulation computer programs such as SPICE. One-port elements. Only 9 types of element memristor not included, 5 passive and 4 active, are required to model any electrical component or circuit. Each element is defined by a relation between the state variables of the network: current, I, display style I, voltage, V, display style V, charge, Q, display style Q, and magnetic flux, pH, display style phi. Two sources. Current source, measured in amperes, produces a current in a conductor. Affects charge according to the relation dq equals I dt display style dq equals I dt. Voltage source, measured in volts, produces a potential difference between 2 points. Affects magnetic flux according to the relation dph equals v dt display style d phi equals v dt. pH display style phi. In this relationship does not necessarily represent anything physically meaningful. In the case of the current generator, Q display style Q, the time integral of current represents the quantity of electric charge physically delivered by the generator. Here, pH display style phi is the time integral of voltage, but whether or not that represents a physical quantity depends on the nature of the voltage source. For a voltage generated by magnetic induction, it is meaningful, but for an electrochemical source, or a voltage that is the output of another circuit, no physical meaning is attached to it. Both these elements are necessarily nonlinear elements. See nonlinear elements below. 3 passive elements. Resistance R display style R, measured in ohms, produces a voltage proportional to the current flowing through the element. Relates voltage and current according to the relation dV equals R di display style dV equals R di. Capacitance C display style C, measured in farads, produces a current proportional to the rate of change of voltage across the element. Relates charge and voltage according to the relation dq equals C dV display style dq equals C dV. Inductance L display style L, measured in henries, produces the magnetic flux proportional to the rate of change of current through the element. Relates flux and current according to the relation dph equals L di display style d phi equals L di. 4 abstract active elements. Voltage-controlled voltage source VCVS generates a voltage based on another voltage with respect to a specified gain. Has infinite input impedance and zero output impedance. Voltage-controlled current source VCCS generates a current based on a voltage elsewhere in the circuit with respect to a specified gain. Used to model field effect transistors and vacuum tubes. Has infinite input impedance and infinite output impedance. The gain is characterized by a transfer conductance which will have units of Siemens. Current-controlled voltage source CCVS generates a voltage based on an input current elsewhere in the circuit with respect to a specified gain. Has zero input impedance and zero output impedance. Used to model transistors. The gain is characterized by a transfer impedance which will have units of ohms. Current-controlled current source CCCS generates a current based on an input current and a specified gain. Used to model bipolar junction transistors. Has zero input impedance and infinite output impedance. These 4 elements are examples of 2-port elements. Nonlinear elements. In reality, all circuit components are nonlinear and can only be approximated to linear over a certain range. To more exactly describe the passive elements, their constitutive relation is used instead of simple proportionality. From any two of the circuit variables, there are six constitutive relations that can be formed. From this, it is supposed that there is a theoretical fourth passive element, since there are only 5 elements in total, not including the various dependent sources found in linear network analysis. This additional element is called memristor. It only has any meaning as a time-dependent nonlinear element. As a time-independent linear element, it reduces to a regular resistor. Hence, it is not included in linear time-invariant LTI circuit models. The constitutive relations of the passive elements are given by resistance, constitutive relation defined as F V I equals 0 / display style FV I equals 0. Capacitance, constitutive relation defined as F V Q equals 0 / display style FVQ equals 0. Inductance, constitutive relation defined as F PH I equals 0 / display style F phi I equals 0. Memristance, constitutive relation defined as F PH Q equals 0 / display style F phi Q equals 0, where F X Y / display style Fx Y is an arbitrary function of two variables. In some special cases, the constitutive relation simplifies to a function of one variable. This is the case for all linear elements, but also, for example, an ideal diode, which in circuit theory terms is a nonlinear resistor, has a constitutive relation of the form V equals F I / display style V equals Fi. Both independent voltage and independent current sources can be considered nonlinear resistors under this definition. The fourth passive element, the memristor, was proposed by Leon Chua in a 1971 paper, but a physical component demonstrating memristance was not created until 37 years later. It was reported on April 30, 2008, that a working memristor had been developed by a team at HV Labs led by scientist R. Stanley Williams. With the advent of the memristor, each pairing of the 4 variables can now be related. There are also 2 special nonlinear elements which are sometimes used in analysis, but which are not the ideal counterpart of any real component. Nulator, defined as V equals I equals 0 / display style V equals I equals 0. Norator, defined as an element which places no restrictions on voltage and current whatsoever. These are sometimes used in models of components with more than 2 terminals, transistors for instance. 2-port elements. All the above are 2-terminal or 1-port elements with the exception of the dependent sources. There are 2 lossless passive linear 2-port elements that are normally introduced into network analysis. Their constitutive relations in matrix notation are transformer V 1 I 2 equals 0 N 0 I 1 V 2 / display style / begin B matrix V1 / I2 / and B matrix equals / begin B matrix 0 and n backslash nn 0 backslash end b matrix backslash begin b matrix I1 backslash v2 backslash end b matrix. Gyrator v1 v2 equals 0 r 0 I1 I2 backslash display style backslash begin b matrix v1 backslash v2 backslash end b matrix equals backslash begin b matrix 0 and r backslash rn 0 backslash end b matrix backslash begin b matrix I1 backslash I2 backslash end b matrix. The transformer maps a voltage at one port to a voltage at the other in a ratio of n. The current between the same two ports is mapped by 1/n. The gyrator, on the other hand, maps a voltage at one port to a current at the other. Likewise, currents are mapped to voltages. The quantity R in the matrix is in units of resistance. The gyrator is a necessary element in analysis because it is not reciprocal. Networks built from the basic linear elements only are obliged to be reciprocal and so cannot be used by themselves to represent a non-reciprocal system. It is not essential, however, to have both the transformer and gyrator. Two gyrators in cascade are equivalent to a transformer, but the transformer is usually retained for convenience. Introduction of the gyrator also makes either capacitance or inductance non-essential, since a gyrator terminated with one of these at port 2 will be equivalent to the other at port 1. However, transformer, capacitance, and inductance are normally retained in analysis because they are the ideal properties of the basic physical components transformer, inductor, and capacitor, whereas a practical gyrator must be constructed as an active circuit. Examples. The following are examples of representation of components by way of electrical elements. On a first degree of approximation, a battery is represented by a voltage source. A more refined model also includes a resistance in series with the voltage source to represent the battery's internal resistance, which results in the battery heating and the voltage dropping when in use. A current source in parallel may be added to represent its leakage, which discharges the battery over a long period of time. On a first degree of approximation, a resistor is represented by a resistance. A more refined model also includes a series inductance to represent the effects of its lead inductance. Resistors constructed as a spiral have more significant inductance. A capacitance in parallel may be added to represent the capacitive effect of the proximity of the resistor leads to each other. A wire can be represented as a low-value resistor. Current sources are more often used when representing semiconductors. For example, on a first degree of approximation, a bipolar transistor may be represented by a variable current source that is controlled by the input current.